Hello everyone, welcome back. My name is Timothy Lee Grant and we are going to be doing another Leetcoding video. So as we've been doing in the previous videos, this one is going to be more calm. I'm not going to be so intense. The idea is just to give us a wide breadth of different problems and try to make the algorithm seep into our subconscious. We're not trying to say, we will understand this, we will solve it. We're going to try to solve it. If we solve it, that's wonderful. If we don't solve it, that's fine. We're going to then go look at the correct solution, see, oh, that's how they did it. Interesting, cool. And then we're going to move on, right? This is not intense. We're not, oh, we have to solve it. No. We're just having fun, okay? So, question is, what do we want to choose? What should we do? We did a counting yesterday. We could do a graph. How does a graph sound? Let's see that. Okay. I'm not seeing many easies here. Here's an easy. All right, let's try it out. 997. Find the town judge. Okay. In a town, there are n people labeled from 1 to n. Okay? So it's not 0 indexed, it's 1 indexed, and we go from 1 to n. Okay? There is a rumor that one of these people is secretly the town judge. Okay, so he's hiding. If the town judge exists, then the town judge trusts nobody. Okay? Everyone except the town judge trusts the town judge. Okay? There is exactly one person that satisfies properties 1 and 2. Okay. Okay. So I think what's going to happen is we have a graph. I see how this is a graph problem. Not quite sure how to actually implement it yet, but I'm just trying to get the overview of what the problem is asking and kind of map it to the inputs that we're given, right? So I think what we're going to have is a graph, and we're going to have edges from one node to the other nodes, and we need to find, and okay, so this should be a directed graph, right? Because it's node A trusts node B, but that doesn't necessarily mean node B trusts node A. And in fact, this judge is going to have all nodes attached to them, but they are not going to be attached to anyone. Okay? So you are given an array trust, where trust of I represents that the person labeled A of I trusts the person labeled B of I. Okay? If a trust relationship does not exist in trust arrays, then such a trust relationship does not exist. Okay? Return the label of the town judge if the town judge exists and can be identified, or return -1 otherwise. Okay, so so we have something called trust. So I'm gonna trust, and what I kind of noticed is sometimes it does help me to just write out in the comments an example of what we're gonna have. I know that they give examples here, but a lot of times it's very simple, like simplified. And you can't dynamically change it because sometimes they say, well, what if this was, and see, I can't change it. So I kind of like to just in the comments before I start, just write out what I think the input or the data structure that I'm going to be working with kind of is, and sometimes it helps me think like, oh, I think I can solve it this way. Because right now I don't exactly know how I'm going to solve it, so let's see. Like, this is just going to be a number though, so 1, so does the number, does this I, so does this index correspond to an actual person? So is there a... No, so what I'm asking is I have this two-dimensional array and it has a list of lists, right? That's what a two-dimensional array is. What I'm curious is, okay, this first element in my 2D array, let me fully highlight it, this one right here, it's at index 0. Does that index 0 correspond to this, like to a specific person? And I think the answer is no, because, well, first off, look, this is index 0, and this starts at 1, so there is no 0th person. Secondly, each index, or each element, I'll call it, has 2 values in it, and those values are representing, like, this means person 1, trust person 2, right? A trust person, okay, A trust B, yep, so person 1 trusts person 2, and that's what corresponds to this in here, not, so this placement gives us no information. It could have been that this was actually here in the middle, kind of like that. So, all right, so let's do another one. Person, I don't know, 3 trust person 2, person 2 trust person 4, person 1 trust person 3, person 3 trust person 1. So how would I even go about doing this? So what is this called? It's called an adjacency list, right? There's adjacency matrix, there's adjacency list, and then there's, what it was, like an edge list? This might be an edge list. And I remember traversing graphs, you normally need to take one. I forget which one of those 3, but there's 2 that are easy for traversing graphs, and one of them is difficult for traversing graphs. And when you're doing these graph functions, or graph problems, you have to normally take that third one and transform it into either the second or the first one. I just forgot which one was which. But, I mean, that's kind of why we're doing these problems, is after this video, we're going to understand that. So, how would I do this? So, can I do, like, possibly a double for loop where I keep track of each of the... That's not gonna work. Oof. I'm a little bit stumped on this one. Well, can I... Ooh. Didn't mean to do that. Okay, let me... I don't know, can I do, like, traverse? Right now I'm just writing stuff to see if I can think of anything. So traverse, maybe, and I have node. Does that help me? Def. Can I do, like, a recursion? I don't think so. Because when I'm thinking graphs, I'm like, can I do depth first search? Um, I feel like this is a pretty good problem though. Like in terms of what I am expecting to be able to learn in the next like 30 minutes or however long this is going to take, I'm expecting that there's going to be a fair amount of progress. So, all right, this is a good problem. It's not one of those problems that is very niche and there's not much application and you learn one little trick. Like I feel like this problem is fairly fundamental to a large section of coding, which is graphs. And this is a directed graph, okay? This is working with those adjacency lists and matrices, maybe. And trying to find what would the judge be classified as? It was like I remember that there's a word like a graph or a node that's not connected or something like that. Hmm. Okay, maybe if I just try to change this into a different format, I can think about it. So, okay, let me go back to the doing some notes. So I'm gonna say connections is going to equal, and how do I want to store the connections? Now I do want the index to offer me some information. What I'm thinking about is kind of like this, where this is the 0th index, which would represent number 1. So I'm just going to do index plus 1, essentially, represents the person. And now I'm going to come through here and see who is number 1. So this number 1 has a connection to it. No, I want to look at the second one, right? So 3 is connected to 1. Or because this is a directed graph, I'm trying to figure out, do I want to go from like this is person 1, right? Do I want to go person 1 is connected to person B, or do I want when person B is connected to person A, right? How does that work? So let's just I don't know. Okay, think about this. Think about it. How does this help me? How am I going to use it to solve this problem? What data structure would be most helpful, or what format would be most helpful for this problem? Well, if so the judge has all nodes connected to it, but it is not connected to anyone. It has no connections. So can I have like 2? So connection trust and connection trusted, kind of like this, where this one is who the person trusts. Okay, so person 1 trusts person 2. So person 1 trusts person 2. So there's going to be a 2 in here. Person 1 trusts person 3. Okay, so 3 is going to be in here. Next one. This one is for person 2. So 3 trusts 2. 3 trusts 2, right? No, that's trusted. Sorry. Who does 2 trust? 2 trusts 4. Right there. And that's it. Okay. This is person 3. Connection trust. So 3 trusts 2. And 3 trusts 1 right here. Okay. Now person 4. 4 doesn't trust anyone. So this is kind of blank. Okay. Trusted. 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 This is the other way around. So this means who trusts person 1, right? 2 trusts 1. So 2 trusts 1. No. I feel like I'm having a, like, you know when you have to invert things multiple times and your brain just gets all confused? I feel like that's what's going on right now. Okay. Trusted. What does that mean? That means this person trusts this person. So this person is trusted by this person, right? So this person, person 1, is trusted by this person, person 3. 3. Okay? Second one, person number 2. 2 is trusted by 1, and 2 is trusted by 3. So 1 and 3. Okay? Now 3. 3 is trusted by 1, and that's it. Okay? 4. 4 is trusted by 2. Okay? So now what I'm thinking is I need to loop through the trusted connections and see if any of them are empty. Because remember, it says that everyone, or the judge town, trusts nobody. So trusted should be empty. But there can be multiple people who trust no one, because both conditions need to be true for the person to qualify as judge. Okay? So we could have multiple people that don't trust anyone. Or this town is just very not trusting, and everyone in the town trusts no one. And then both of these are empty. And notice that would mean that everyone trusts the town judge. So if there exists a town judge, then everyone would be trusting that person. But if no one trusts anyone, then that means that there is no town judge. So we can return -1. So what I'm thinking about doing is kind of trying to create these two arrays, then looking for in here an empty list, which would indicate that this person does not trust anyone else. Okay? So the judge town trusts nobody. That satisfies that condition. Then this is my candidate. I say, okay, you're a candidate. You might be a judge, or you might not be. Let's see if you satisfy the second condition, which is, does everyone trust you? So I'm going to go to your specific index. So this is going to be let's just say that this one was empty, right? This one is this index of 1. So I'm going to go to index of 1. And if this contains all of the people, okay, then what I can do is just return that person. This index corresponds to index plus 1 is the person, right? And that person is the judge. So that's how I want to do this. Okay, so let's make these two connection trust, and I'm just going to call it trust and trusted. So equals an empty list. Trusted is also an empty list. Now I'm going to, okay, so for element in trust. Ooh, trust is here. I don't like that. Can I just do that? Trust 1. I don't want to change this one. I like this one, and I'm going to be using it a little bit more often. So I've just changed up here. Okay, so element. What is element going to look like? Element is going to look like something like this. So it is going to be one of these particular things. A trust relationship, and it's only going to have 2. It's not going to have multiple things in here. So okay, notice I did these two kind of incorrectly. So what I want to actually have at the beginning is not an empty list, but an empty list containing empty lists of how many in here? N of them. Because this represents person zero's people who he trusts. Who does person 1, who does person 1 trust? Who does person 2 trust? Who does person 3 trust? Who does person 4 trust, right? So I want all of these up to 4 if n equals 4. So how do we do that in Python? So we have that for, and for what? For blank, because I'm not using anything, in range n. Okay, so I'm going to get n of them. And what do I want to do? I want to, oh, not a dictionary. I want to have this empty list. And then same thing for down here. So for don't care in range n. So I'm just creating a list of empty lists. And how many empty lists do we have? We have n of them. Okay, so now when I get this, like element, which is 3, 2, So this represents A truss B. So this means 3 truss 2. Okay. All right. So it's getting warm. Jacket off. Okay. Well, let's start writing it and see what's trust. I want to append trust. So if I have one of these, I know that there is a person, that there's 2 relations that I need to add, right? So I'm going to say trust dot append. No, I don't want to append. I want to index. Which one do I want to index? I know that I'm going to be doing element, so it's one of those 2 relationships here, but which one? So I want to, in here, I want to say this element and change this to correspond to what I said, trust and trusted. Okay. So I said this one corresponds to person. So the index is the person who trusts. So 3 trusts. So 3 is 0th index. Yeah. So 3 will pull out this number here. So then I'm going to get element of the 0th index, which is 3. Okay, and then I'm going to change my trust. So I'm getting this third one here. Truss 2. Now this is dot append element 1. So now I want to index this third. So 0, 1, 2 here. Actually, do I want, I might need a -1. I might need to do a -1. The reason that I'm saying that I might need to do a -1 is because each of these numbers in the trust array is person, which is 1 indexed, not 0 indexed. So I might need to say, okay, if it says 0 and 2, that actually means the 0th index. Person 1 corresponds to the 0th index, right? So I just need to take whatever they tell me in the trust and then subtract 1, and I get the index. Okay, so I'm getting this 3, 2. This means 3 truss 2. Yeah? And in my trust, I want index 3. Well, actually, index 2, right? So 0, 1, 2. And now I want to append, because as of right now, this is empty, right? All of these are empty. And I want to append a number. What number do I want to append? I want to append 2. Because 3 truss 2. So I want to say that. So index 3 truss 2. So append the trusted element here. Okay. The element that is being trusted. Okay. Then I want to kind of do the reverse and trusted. Okay. And I want to say 2 is trusted by 3. Okay, so let's do that. So element indexed at 1, so this pulls out this 2. Okay, so then we're indexing that, but we want to do -1. We also need a -1 there. Dot append, and what do we want to append? Element of element of hold on, is the -1 out here, or is it in here? So this 3, well, this 3 is, no, this is element. Why am I thinking like that? This element has 0 index and 1 index. That's what I'm getting with this here. Then I'm passing that in as a parameter to the trusted, and the trusted is that conversion between person and index that has the one-off relationship. So that's why I have to do the -1 out here, because that's indexing. This is just indexing the element within this element, but the index within this element here. Okay. So now I want to say like 2 and then append 3, right? -1. Okay. So I think by the end of that, I'm going to loop through all of the elements and add everything into both trust and trusted. Then what I can do, so for element in trust, okay, so I want to find an empty list. So what I'm going to do is if not element, okay, so that means that this element is empty. Then what do we want to do? We want to okay, candidate, I don't know, candidate judge, okay, pass. I'm not sure what I want to do right now. Otherwise, what do we want to do? Otherwise, we want to disqualify that person. The person's not the judge. If they trust someone, then they're not the judge. We just go to the next element. And then if we ever come out here, we know that the judge does not exist because all elements don't satisfy the condition. And here we need to, so we need to search for second judge criteria. Okay. So I need to see if everyone trusts the town judge. So how do I want to do this? not element. And I think I also need to do enumerate, trust, and then index element. Because the index actually gives me information on who the person is. And then element will be all of the people who that person here trusts. Okay. Well, and I know that there's n of them, right? Maybe what I can do is something like that. Oh, this is not a good thing. So people equals a list and x for x in, I think you guys are seeing where I'm going with this, in range n. So each time I find a candidate, I am going to create a list. Oh, this is not a good solution. This is not a good solution. But we're going to have to try it. I am going to create a list with all of the elements in here. There has to be a way to do like sets. There has to be there has to be there must be a way to do this with sets. I'm just putting that out there. Let's, okay. Now what do I need to do for Ella, so this means that no one trusts, or that this element trusts no one, and this index. So for come on, what is it? For TD, I don't know, to be determined, because I can't think of a name right now. For in trusted, indexed at index, right? Yeah, means this person trusts no one. Now I put this person into the trusted list to see who trusts him. And then I mean, the people dot remove. Oh my goodness. TD. Okay. Then what I can do is if not people, return index +1, because this is the person, or this is the index which the person represents, and then we do +1. I don't think that I think that there must be some logical errors, and this is a completely inefficient solution. I think remove is O of n, which is inside of this, which could be O of n, which is inside of this, which is O of n. So what? That's n cubed. Well, okay, this is only going to run. No, this is. Yeah, this can run n times. This can run n times, right? Jeez. Okay. Let's see if it even. Oh, wrong answer. Well. Hmm. Let me try the run button. Sometimes that gives you more problems. So a pass one test case. Is it returning -1 on everything? Yeah. So I said that I wasn't going to. It's returning -1 on everything. So first I'm going to see if GPT can find any like gaps in my knowledge or logical errors in here. Then I'm going to see how we can make it more efficient, because I think that there has to be a better method. So this is always returning -1. Can you see any errors in my code? You are trying to find a candidate judge by checking if trust list for a person is empty. While this is correct, the second check should ensure that the candidate judge is trusted by exactly n-1 people. Oh yeah, I guess I could do that, right? Like, oh, okay. Come here and say if trusted indexed at index, this length is equal to n-1, then we return index plus 1. Should, like that? Oh, okay. Yeah. Well, we were able to get these different data structures from this data structure. We were able to successfully implement all. I was wondering, like, am I going to get some kind of problem with my indexing? And I kept trying to cross things over back and forth, and I was getting very confused. I was confusing myself, and I was like, is there going to be a problem there? And then, okay, this makes sense. So what we're doing is we're just going to this trusted here, and we're saying if everyone trusts this person who is index 1 corresponding to person 2. So if everyone trusts this person 2, their trusted list is going to contain everyone, obviously accept themselves. Now, how many people are there? There's in people, so there's in, and then -1 because they don't. It's not a trust to themselves, right? So that's why I did that, and this is the second check. Like if the length of this element is in -1 length, then I just return that person because that person satisfies this criteria, which is the town judge trusts nobody, okay? Then this criteria means everyone except the town judge himself trusts the town judge, okay? In -1, and then I just return that person. The person, not the index, right? So the index, but then +1 makes it the person. Okay. Let me see if there's a more efficient solution. Okay, so we are creating a list of all zeros, which is how long? N +1. So, okay, kind of what I was doing here, but instead of empty lists, it's just 0. So, for ij in trust, count of I minus equals 1. Oh, okay, so they're just going to, for I in range, starting at 1, going to n plus 1, so going through all of the people, if count of I equals this n minus I, okay, then we found the person. So if that person I feel like this is not doing a graph, right? This is kind of like a trick. I'm not looking for a trick right now. Let me see. What are the 3 types of, what are the different types? I'm not going to give it 3 because then it's going to kind of like put that idea in its head of 3, and then even if there's 4, it's not going to tell me. So what are the different types of representations of graphs that like the data structures? Okay, because I said adjacency matrix, adjacency list, and then I was like, okay, so adjacency matrix. Take some. Fortunately, it's not coffee. I don't have any coffee today. This is caffeinated tea, so trying to save off the headache. Okay, so adjacency matrix is a 2D array where the rows and columns represent vertices and the cell at the intersection indicates whether there's an edge between them, okay? So this can also be used for directed, okay? Adjacency list is a graph. Each index of the array represents a vertex. That means node, right? And the list at each index contains the vertices that are adjacent to it. Sure. Edge list. Incident matrix. Where the row represents vertices and the columns represent edges. Okay, so there's a little bit more that I didn't know about. And so each of these have different pros and cons based off of like the size, the connection space, all of that. Okay, so in my implementation, what would trust and trusted be? Okay. So your implement are lists that store the trust relationship. So is there not like so it's not one of these specific things right here, I guess maybe. Um okay, so I guess next steps moving forward for me is I should probably kind of look through these. I think I understand adjacency matrix. It's just this row is with this column, and that means that there's a connection. Um, well, actually, I don't. If they're, how would I represent a directed graph? Do I choose like the top one to be the connection from here, and then this one is to there? So from here to there. Maybe that's how. Okay. Then I need to figure out like, okay, what is an adjacency list and why is it different? I thought I was doing an adjacency list here. I thought that these were adjacency lists, but apparently not. Edge list. Edge list represents a graph as a list of edges. Each edge is a tuple of two vertices, indicating an edge between. Oh, I think that that's actually what this is, right? This is an edge list because it's saying here to here, right? Yeah, I think that this is. I think this is an edge list. That's what I was trying to say. Like adjacency matrix, adjacency list, and edge list. I think this is an edge list, and the edge list is the one that you normally need to convert either into an adjacency list or an adjacency matrix. Okay. And I still think that this is an adjacency list. I think it is, right? It should be. It should be because adjacency list is this element is connected to these two elements. This element is connected to this element. This element is connected to this element. I think this is I just did two different adjacency lists, but I said what connected means is different based off of like is this one way or is it the other. So I think that this is adjacency list. This is an adjacency list, and this is an edge list. Yeah. Okay. And then we don't need to do anything with sets because this is already efficient right here. Okay, so there we go. Well, thank you guys for watching this video. I hope you enjoyed the journey. I certainly did. This was fun. I learned a fair amount about graphs, and I feel like we were able to make some really good progress on this problem. Obviously, this little idea right here didn't immediately come to me when doing the solution, but now I've seen it and now I can think about it a little bit better, and hopefully next time we come across a problem like this, bam, it's down in my subconscious and I'm able to pull it up. Just like what happened yesterday. I saw a problem that I had previously tried to solve, and I failed to solve it a long time ago. And then I looked at it yesterday, and the problem was actually obvious to me. Like, I didn't really have to think about it. I just, oh, okay, well, I can do it like this. And then I pressed submit, and it was accepted. I was like, oh, wow, okay. Even though I didn't think I was getting better, I actually was. Right? So I think that there's a lot of merit to just getting repetition and seeing different things, like doing this. It didn't immediately come to me now, but next time maybe it will. And so, yeah, thank you guys for watching this video. My name is Timothy Lee Grant, and I will see you guys in the next video where I do another Leetcoding video every day doing Leetcode. So if that's interesting to you, subscribe. If it's not, then that's okay as well. I will see you guys tomorrow.